my project is based on using GANs to generate synthetic ultrasound data, 3D data, together with anatomical labels for that data. So the main motivation behind my project is that these days there are a lot of AI models trying to be commercialized, but there's a lack of publicly available data sets, especially on 3D echocardiography. There is no public available data set. So in order to develop deep learning algorithms to help clinicians to get to the final diagnosis and to save them time, those AI algorithms need to be trained with medical data, which is what we are lacking. So I've been training GANs, 3D GANs, to generate 3D echocardiography images, which can then be used to train deep learning algorithms for the most varied tasks, such as segmentation, for example. So this is my pipeline. This is what I've been doing. So I'm training a 3D GAN under a paired scenario, which means that I'm training the GAN with two image domains, and these two domains are related to each other, they're paired. So I'm using real 3D echocardiography volumes that are already existent, and then I use anatomical labels which correspond to these 3D volumes. These anatomical labels are done on a first step by a cardiologist, which is one of the other ESRs in our Marcius project. So this is, you can see that our projects are actually all linked, and we depend on each other to do our own projects. So having these two dependent data sets with images and labels, I train the GAN, and then at inference, I generate 3D synthetic data sets. So I take 3D heart models. These ones were acquired with CT, and I extract these anatomical labels, and I generate a corresponding synthetic image using the trained GAN. And then to prove the utility of such type of images, I've been training 3D segmentation models using different synthetic data sets. I don't know if you guys are familiar with it or ever heard of it, but the GAN that I'm using, it's the PIX2PIX model. So this is a paired GAN. Like I mentioned, the images on both training domains are related. And what I've been doing is I took the original work, which is the one you can see here on this figure. So you always have, you can have different domains, A and B. You can generate different types of images depending on what you're trying to generate. So I took the original GAN and made it 3D, deal with 3D images. And the two training domains that I use are the real images and the anatomical labels. And the working principle of a GAN is to minimize the generator loss and to maximize the discriminator loss. So the generator tries to fool the discriminator all the time, but the discriminator cannot be fooled. That's why it maximizes its loss. So when you reach this point during training, then you have hopefully properly working GAN. Regarding the data that I've been using, so all the real 3D images were acquired with GE ultrasound scanners, and they were sliced like this, like you can see here on the top. The gray cone, it's not very well visible, sorry for that, but the gray cone represents the volume, the echocardiography volume, and then the yellow planes represent the slices, the way the volumes were sliced at different angles. So it looks more or less like this. And then all these images were then again annotated by cardiologists, which is part of our project. And these gray level masks were generated corresponding to each of the 30 training volumes that I used. So during training, this is a 3D GAN And the 3 dimensions that I'm talking about are the spatial dimensions. So it's not 2D plus time. So all the volumes were acquired during end diastole. So it's a fixed point in time. And the 3 dimensions that I'm trying to predict, let's say, or to generate are just spatial dimensions. Here I've been focused only on the left ventricle, the left atrium, and the myocardium, which are these 3 structures you can see on the labels. But this approach is generalized. You can generalize it to any other structure you would like to include in the synthetic images. So I trained this GAN during 600 epochs, and it took around 5 to 6 days to train it because it's 3D data. And I was having some computational memory constraints, as it's obvious. And these are 2 of the best training epochs. And you can see on the column, on the first column is the original real image. In the middle, you have the anatomical label corresponding to this real image. And then on the last column, the column on the right, you can see the synthetic image. So the one that provides the best commitment between a minimum generator loss and a maximized discriminator loss. So this is the results from training. And after this, I was using the GAN to synthesize images. So I took these 3D models of the heart, which were acquired with CT, and I sliced them to get the anatomical labels and used these labels as input to generate synthetic images, which looked like this. But a very common problem when dealing with GANs is the checkerboard artifact, which reflects on checkerboard pattern, which is always present on the generated images. And to remove that, I added a step of denoising to make that checkerboard pattern less visible. And another thing that was occurring on the synthetic images are these small areas which are not present on real 3D echo images. So to remove these, I applied a cone fixing step to remove these to make the cone edges less wavy, let's say. It would look like this in the end, more straight. At inference, I used around 30 CT volumes, and I generated synthetic images for them following that same principle of slicing and getting the gray level images and then generating the corresponding synthetic ultrasound image. And like I said, these images now need to be validated. And the way we validate it is to prove that they can be useful to train deep learning algorithms. So I created a training scheme, let's say, of 3D segmentation models using several different synthetic data sets. So from my original GAN, the 3D peaks-to-peaks model, I have direct synthetic data sets without any post-processing operation, which is this one, first one. And I train segmentation model on this simple data set. But then I apply to this synthetic data set, I apply the different post-processing operations to evaluate until which point these operations actually influence the final outcome when it comes to segmentation of those of the left ventricle, the left atrium, and the myocardium. And with these 3 other data sets, I trained another 3 segmentation models. Then to inference or to make conclusions about using this synthetic data as a data augmentation tool, for example, I create these data sets that contain real data mixed with synthetic data. And then again, I train segmentation models on these mixed data sets to evaluate the power of this GAN as a data augmentation tool. I don't have results to show you from the segmentation models because it's still a work in progress and it's still training. But from some previous work that I've done, it looks like the cone post-processing operation, the one that fixes the edges of the cone, has less relevance comparing to the wavelet denoising transformation. So the wavelet is actually relevant. So it provides more accurate, the segmentations from this model, the model that was trained on the wavelet data, provides more accurate segmentations than the model trained on data which had the cone reshaping transformation. And some of my previous results also show that including real data together with synthetic data also improves the final segmentation. So those are some initial results that I have. I cannot show you more now because I don't have them, but this is the main idea behind my project, to train the GAN and use it to generate data. There are no public data sets available out there, especially on 3D echo image.